This lecture explains the laboratory exercise, Newton's second law. For those of you enrolled in Conceptual Physics AB, I present this lab to you as a mini lab exercise. For those of you enrolled in Physics AB, Honors Physics AB, and AP Physics C, you are to write a laboratory report of this exercise. Okay, so let me take you through the lab. Newton's second law. Okay, let me describe the theory, first of all, behind the laboratory exercise. The theory behind the laboratory exercise is the problem involving the basic air track that I went through in lecture. Let me once again refresh your memories of that problem. Okay, so we have the air track like so. The air track is horizontal and frictionless. Okay, right here is the air track cart of mass M1. Then we have the string draped over the pulley. Right here is the mass M2. Okay, M2 is equal to 500 grams. And then in my short video where I actually obtained data for this laboratory exercise, I show you how I measure the mass of the cart M1. I've posted for you a picture of the mass of that cart in today's folder. So M1 is also measured and it's given. Okay, then all that we simply do is we turn on the air and we then release the system such that it accelerates like so. Okay, now in the course of doing the problem involving the basic air track, I derived for us the following equation. The acceleration is equal to m2g divided by m1 plus m2. For those of you enrolled in the classes that are writing a laboratory report for this exercise, what I need to see in the first section of your laboratory report is the derivation of this equation. I went through that derivation of the equation in the problem associated with the basic air track. However, you have to provide for me that derivation in the first section of your laboratory report. The reason for that is because you always develop the theory behind an experiment in the first section of your laboratory report. Therefore, you have to include that derivation there. Okay, now for purposes of this lab, we're going to refer to this acceleration as the theoretical acceleration. We're going to call this a theory. Okay, and then once again, the basic idea behind this experiment, very simply, is that we're going to measure the acceleration by using a spark timer, and we'll then compare that measured acceleration to, in theory, what it should be, which is this quantity here. That's the theory behind the laboratory report. Okay, or the laboratory exercise. Okay, now let's go ahead and run through the procedure. Okay, so for the procedure then, I set up the situation as is described on the top board, and then I did the following. Okay, so here's my cart, the string, the pulley, the other object off to the side. And then what I did was I took a length of strip tape and I taped it to the top of the cart like so, and I threaded it through the spark timer, which is back here. Okay, and then right over here off to the side, I have my air source like so. And then what I did very simply was I turned on the air, I turned on the timer, and then I let it go such that it accelerates once again like this. Okay, and then I've photographed for you the strip tape that I obtained for this laboratory exercise. Here's then how you analyze that strip tape. We do it exactly the same way as we did for the free fall laboratory exercise back in the unit on kinematics. Okay, let me do some erasing here. Okay, so let's say that right here is the strip tape like so that I obtained. And there's always a little bit of smear at the beginning. That smear then corresponds to the time between me turning on the air and turning on the timer prior to letting go of the object. But once I do let go of the glider, the cart that is M1, then it accelerates across the air track. This then means that the dots will get progressively further and further apart as the cart accelerates. And then what I did is I chose a dot close to the beginning of the tape as my origin. I labeled it as such, and then I numbered 1, 2, and so on, ultimately out to a dot 9. So we have 10 total dots here, dots 0 through 10. Okay, and then you start to construct the following data table. Okay, so first of all, we have here dot number. We use the letter N as an index to indicate that. That is, N is equal to 0, 1, 2, 3, and so on, out to a dot 9. Okay, and then the next column is going to be the position of the nth dot in terms of meters. So you can go ahead and measure in terms of centimeters, but do make sure that you divide by 100 to convert to meters here when you tabulate the positions. And then recall how you measure the position on this strip tape. You measure from dot 0, so from 0 to 1, 0 to 2, 0 to 3, and so on. Once again, you can measure in centimeters, but make sure you divide by 100 to convert to meters. Okay, and then the next column is the time at the nth dot in terms of seconds. Recall that the frequency of the spark timer is 60 hertz. It makes 60 dots per second, so then therefore the time interval between the dots is 1/60th of a second. So then therefore if we start the clock at dot 0, then for dot 1 it's 1/60th of a second, for dot 2, 2/60ths of a second, and so on. And then the last column is the velocity at the nth dot in terms of meters per second. And we use the following formula, just like we did in the free fall laboratory exercise, to find the velocities. The velocity at the nth dot is equal to the position of the dot ahead of it minus the position of the dot behind it divided by the time interval between the n+1 and the n-1 dots. Now recall the example that I always use to illustrate the use of this expression. So for example, let's say that you have to find the speed or the velocity at the 6th dot. So then what you do is you take the position of the dot ahead of it, the position of the 7th dot, and you subtract from that then the position of the dot behind it, which is the 5th dot. You're then always dividing by the same quantity here, 2 times 1/60th of a second, 2/60ths of a second. That's the time interval between dot 5, for example, and dot 7. Recall that there is a little bit of a shortcut here. The shortcut here is that instead of dividing by 2/60ths of a second every single time, you could just multiply the numerator of the expression by 30. So recall that shortcut. Also recall that you cannot use the formula for dot 0, and the reason for that is because you don't have a dot -1. So then therefore you just put a slash here on your data table for dot 0, nor can you calculate the velocity at dot 9 using this formula because you don't have a dot 10. So basically you calculate this then for dots 1 through 8. Okay, and then to find the acceleration, we plot the following graph. Okay, so you put the time here at the nth dot in terms of seconds on the horizontal axis, and then scale your axis when you plot your graph in the following way. Skip a space and then say 1/60th of a second, skip a space 2/60ths of a second, and so on. And then here along the vertical axis, this is where you plot the velocity at the nth dot in terms of meters per second. So based upon what you measure for dots 1 through 8, make sure that you scale your axis on your graph accordingly. Okay, when you do plot your points, they will very obviously be linear. So then therefore you take a ruler. I'm going to grab my ruler here. You then take your ruler and you fit it up to your points, like so. And then you draw a best fit line. And then with that best fit line, what we need to find is the slope of that line. So you have to pick 2 points that are on the line. They could either be 2 data points, or you can use, for example, a corner on your graph paper that the line intersects, so you can easily write down what the ordered pair is for that point. Suffice it to say, however, you then calculate rise over run. So the rise is the change in the vertical axis, the run is the change in the horizontal axis, and you then calculate the slope as rise over run. Okay, when you do this, by the way, be careful of the run being in terms of 60ths of a second. Okay, then when you do calculate this slope, the slope is equal to what we're going to call a measured. The units are going to be in terms of meters per second squared. Now, in theory, A measured should be the same thing as what we had determined earlier. It should be the same thing as A theory. Recall what A theory is. Okay, let me do some erasing. A theory, remember, was the following quantity. So what you have to do at this point is you have to calculate A theory. The mass M2 is 500 grams, that's half of a kilogram. And then I gave you the mass M1 in the folder. Make sure that you write the mass M1 in terms of kilograms when you plug it here into this formula, and G, of course, is 9.8 meters per second squared. So when you calculate A theory, it's also going to be in terms of meters per second squared. In theory, A theory should be the same thing as A measured. So then the last step then is to calculate a percent error. Your percent error is as follows. You take the absolute value of the difference between A theory and A measured, and then we'll make the comparison with respect to A theory. You place that in the denominator of the expression. What you'll end up with here is a decimal. Make sure that you multiply by 100 in order to convert it into a percentage. Okay, now for those of you that are instructed to construct a formal laboratory report for this exercise, what you have to do after your analysis is you have to go through the errors. Besides calculating the percent error as I'm doing here, we also have the following qualitative sources of error. We are assuming that the error track is horizontal. It may not quite be because all that I did was I placed it on the desk when I obtained data. In addition to that, we're assuming, of course, that the surface of the error track is frictionless. There's no such thing as a frictionless surface. There's also friction between the strip tape itself and the spark timer that is completely unavoidable. So then therefore, based upon those errors, how do you know whether or not you got a good result when you write up your conclusion? Well, a good rule of thumb when it comes to doing these spark timer laboratory exercises is that if you calculate a percent error that is less than 10%, then that's a pretty good result. However, if it just so happens that you end up with a higher percentage error than 10%, then in your conclusion, can you honestly say as to whether or not you have fulfilled the experiment's requirements? The answer to that question is no. So then therefore, if you're forced to conclude that no, we did not verify Newton's second law with this laboratory exercise, as long as you understand the reasons why that is an error analysis and you state it as such, then that is perfectly acceptable for your laboratory report. As I previously have mentioned, when it comes to laboratory reports, I'm really not so concerned with getting the correct result. Instead, what I'm more concerned with is that we do the scientific method correctly. So keep that in mind when you write up your laboratory reports. Make sure that you follow the general guidelines for laboratory reports. I have posted that for you in today's folder as well.